Electric. Thank you.
Thank you. Well, good afternoon, gentlemen. Wanted to welcome you to the composite stage and to our presentation on voltage detection and indication. As you'll notice, this says Bill McNulty. I'm not Bill McNulty, I'm Jeff Gould. I'm one of the regional managers for HD Electric. Bill McNulty is our technical director and is the one that wrote this paper. What we want to talk about this afternoon is very important that you pick up on two words here, voltage detection and indication, because there's also voltage measurement, and we'll talk a little bit about the differences in those as we go along. As you see here in the picture, what we're showing there is a voltage measurement. The distinguishing part of a voltage measurement is, you'll notice that that's a two-stick operation. We have a probe that contacts the conductor. We also have a reference to ground. So we're doing a voltage measurement here. Wired voltmeters, still the most common in the industry, still the most accurate. Loads the line and can discharge a stored charge on a line. It's not the most convenient. What do we mean there? It's a two-stick operation. In a lot of the utilities, that requires a two-man operation there if you've got two sticks. Also can be a safety issue because we are coming in contact with ground on a live line. Froze up. There we go. So what is the next generation of voltage detection and why has this come into play? We mentioned the safety issue, convenience. Now it's a one-man operation. There's no distance there because there's no cord required. It's one piece, reliability, pretty much the same as our voltmeters. And accuracy. What is that accuracy? Now we have to begin to separate our intentions here. Are we looking for a voltage measurement? Or are we looking to understand and detect or indicate voltage on a conductor? Is it on? Is it off? Is it at line voltage? Is there induced voltage present? Or maybe we have some backfeed. So in the next generation of voltage detection, what we're doing is we're actually measuring the electric field. As you can see in this picture, we've got a tower there with a big halo there indicating the electric field off of an energized transmission line. We've also got a distribution pole there, and you can see by the graphic the strength of the electric field and the difference in that electric field, the electric field being that's shown in red. We're going to talk about making measurements or making indication and detection in those two areas. Electric fields surround every energized conductor. They are not affected by insulation. What do I mean by that? I've got two different cables here that we commonly use in the industry. I have just a typical secondary wire where what you see is all it has on it is the insulation. The electric field is still present around a cable of this nature. When we get into direct buried primary cable, what we've done is we've created our own worst enemy in some ways when it comes to voltage detection and indication. From a safety standpoint, it's very safe. What you'll notice is I've got the primary conductor down the center, surrounded by a semicon, surrounded by the concentric neutral, and then I have the insulation on it. And effectively what we've done by putting the concentric neutral around our primary conductor is we made it virtually impossible out at center span or somewhere along the cable to actually indicate or detect voltage on that. So we have to use alternate methods back at the connection points to determine whether a cable is energized or not on our primary cable. It will, however, the devices we talk about will measure the electric field around a cable like this. Field strength is proportional to voltage and distance. The electric fields on the cable, closer to the cable we are, the stronger the electric field, and the further away we start to get. And we'll see that in this graphic, and then we also see it in this graph here, where distance, the further away, the closer we are to the cable, the stronger the electric field, the easier it is for us to indicate and detect at that point. And as we move out the cable, we get very weak field measurements. There are some instances when that weak field measurement can play to our advantage as well. One of the products that we have in our offering is, you see here in this picture, a gentleman with what we call our V-Watch voltage detector. Looks like this. It's designed to be worn around the neck. And what it's designed for is those out of normal work situations where we've had lines down during a storm or something of that nature. We don't know if they're energized or not. So in that case, what we want is something that will detect voltage when we're further away from it and give us a warning so that we don't walk into that energized cable. You'll notice that he's got it on a lanyard which is built into the case here. He's wearing it around his neck, and as he's walking an area, it's looking for those electric field signals to pick up and allow him to not walk into that energized cable. This graphic kind of shows how the V-Watch works as I'm wearing it on the front of my torso and I'm walking forward. The higher the cable and the further the distance based on the voltage of the cable or the voltage of the line. So you'll see in the red what I'm getting there in that darkest red circle. That's my my strongest indication warning, or third warning level, meaning that I have reached that point where if I don't see that energized cable, I need to stop. It's a 3 warning system. So further out, the first one, the yellow, first warning, is a slow beep. The orange circle there, second warning, is a medium beep. It starts to beep a little bit faster, then to a solid tone. Medium distance voltages, or medium distance detections or indications. A lot of times that's where we're operating when we're trying to determine if something is energized or not, whether we can ground the system before we do our work in the field. What we're using for a device like that operates very similarly to on the same principle as our V-Watch. It's a proximity voltage detector. We're not actually contacting the conductor. We're just giving you an indication of voltage as you approach an energized conductor. Where it becomes important there is I want to know if all 3 phases in an overhead system are energized, or if maybe I've got one that's out. When I'm using something like the V-Watch, where it's measuring voltage at a higher detection rate or a higher sensitivity, it would not work in this application because it's going to, if any one of the 3 is energized, it's going to tell me that, yes, something there is energized. So now what I have to do is I have to have the ability to select the range of voltage that I'm expecting to be there and indicate. So as I use something like our PRX 500, if I were on a 69 kV, I would select the 69 kV range, and then I'm going to detect voltage at about 8 to 10 inches, which gives me that flexibility now in that electric field measurement to say, okay, phase A is energized, phase B is energized, but phase C is offline. So what I've done is effectively shortened that detection distance to where I can make some critical decisions in a confined space. Yes?
Would that know the difference between, say, like you're saying like a live source, something live, versus like a wall socket? Like, would that know the difference in strength, you're saying? Like, that would not detect the socket, for example?
Not necessarily, no. It does. It does. It bases it on the strength of the electric field. Now what you'll notice is this is not auto ranging. What I have to do is I have to select the range. It's going to default when I turn it on to 120. That's the most sensitive range. So I could pick up, let's say at that same 69 kV, I could hold it out the window of the truck and say, yes, something on that 69 kV system is on. But now when I start to make my decisions, I'm going to put it on a hot stick. I'm going to select the 69 kV range where I've effectively shortened that sensitivity to where I can make the decisions based on a closer detection. In this, we talk about geometry matters, and we talk about the electric field. This graphic here, what he's simulating here is when we go around bends, when we go around curves, when we get closer to metal apparatus, it starts to distort that electric field. So my warning distance is going to be increased or decreased based on the geometry that's around me. That's true with any of these. As you remember back to that graphic that we talked about on the V-Watch. If the conductor is down close to the ground, but it's still energized, my approach distance wearing the V-Watch is going to be shortened, because what I've effectively done is mushroomed the top or the bottom off of the electric field. As you can see on that outer bend, my electric field is shortened. On an inner bend like that, it's expanded. So I'm going to detect voltage at a little further distance on that inner bend. Strong field measurements. This is where typically HD Electric has operated for the 81 years we've been in business. And what that is that's a contact type device where we're actually measuring voltage by actually contacting the conductor. It's still the most accurate, most reliable method of understanding whether a conductor is energized or not. As you'll see here, we've got, and that graphic is very small, but you can see the hot stick here in the center. Got a gentleman down here holding the hot stick. He's going up to a bus bar in a substation. He's using a detection device similar to this. He's got a bigger hook on it, but we're actually contacting the conductor. We're still using an electric field type measurement here to do that. And one of the ways that you will understand that if you're using this device is when you're in that electric field, whether I have a display on the front of the unit will already be beeping at you to let you know, hey, I'm in an electric field, something around me is energized. But it won't actually give me a reading until I contact the actual conductor.
It won't electrocute you?
It will not. That's correct, because we're on the end of hot stick here. This picture shows he's on cable there, or on a bus bar there. The strong field measurements, when we're talking about detection and indication, contacting the conductor is still the most accurate. We're closest to the conductor, so there is that safety factor that comes back into play, but I'm one stick instead of two sticks. And as I mentioned, geometry still matters. The closer I get to that conductor or the further away I get from that conductor is where it's going to affect me. Electric field measurements can be detected at almost any distance. It's the most accurate closest to the conductor. Geometry matters. Devices must compensate for that geometry. Long distance personal voltage protection. Medium voltage distance is those proximity detectors. This type of detector here. And then the direct contact detectors and indicators. Any questions? Any and all of the electric utilities, contractors that would do hotline work for the electric utilities. So.